Right, this is the first of two videos on the basics of acid-base chemistry. Acid-base chemistry is really just chemistry that describes a reaction between an acid and a base. So in the first thing we'll need to cover is kind of what is an acid and how does that reaction proceed, and what is a base. So we'll cover that, and then we're going to look at types of reactions, or types of acids in those reactions. And then last, we'll look at buffers. So in the second video, we'll focus in on buffers and how they're important to the biological processes for maintaining the pH of the body's system. And we'll look at also what pH is. What's that good for? It's a way to measure acidity. So let's go ahead and look at what is an acid. And it really sort of started, first of all, with the idea of a lone proton, that the proton was donated by an acid and accepted by a base, the proton H+. That's an Arrhenius view. I don't think I got his spelling right, but it really quickly moved forward to, well, most reactions with acids are done in water, and the agent that we really have that carries the positive charge is H3O+. This is more the Bronsted-Lowry view of an acid-base chemistry, an acid-base reaction. So here's what we can say then as we look at a reaction, is that acids do, in general, and this is true, the acids donate protons. In the Bronsted-Lowry view or the Arrhenius view, the acid donates proton. So let's think of this hydrogen chloride then, HCl. In water, it donates a proton to water. Now water then becomes an agent in this reaction, and its role is to accept the proton from HCl. So it's called the base, whatever is accepting that proton. And this is, of course, our acid. There's always those two parts in an acid-base reaction. Someone's donating the proton, and someone's accepting the proton, the base. To make not H+, we don't just donate it to nothing or just kick off a proton. We're donating it to the base, and the base then becomes H3O+, because it accepted that proton. So we make what's called the hydronium ion. You'll hear a lot about that in acid-base reactions, because this is the agent that we really have in solution that reflects acidity. And we make then also the counter ion for HCl, and this is called the conjugate base. Conjugate base, because it's the anion left from the starting acid. So these are some terms, acid, base, conjugate base, that you'll want to know as part of an acid-base reaction. Just some other facts. If we have litmus paper, we can check this solution made between HCl and water. And if it turns the litmus paper red, it's acidic. If it's blue, it's basic. So blue and basic kind of go together. Acids have a sour taste. If it's kind of vinegar would be an example. And they are electrolytes. Remember, we talked about electrolytes. You needed to have charge that can kind of get jiggy with it in aqueous solution when you apply a alternating current. Well, we do have ions. If it's a strong acid, we have a lot of ions, and if it's a weak acid, we have just a few. So just to kind of review, let's kind of circle the acid in this reaction below, and let's underline the base, and maybe we'll box in the conjugate base. So we'll kind of do those parts. So we're going to circle the acid, we're going to underline the base, and we'll box in the conjugate base. So HBr, we notice, looks a lot like HCl, and anytime you have a halogen connected to a hydrogen, it's an acid. So we have the acid here, we'll circle. It's a strong acid, so I'm going to go ahead and just put underneath there that it's a strong acid. That means whatever it's going to do, it does it strongly. It donates a proton to H2O. So this is our base, I'll underline it. This is our base. It accepts that proton to make, again, H3O+, hydronium ion. And this would be our conjugate base that's floating around in solution. So those are sort of the basics of a Bronsted-Lowry acid-base reaction. And we can go quickly now because we know what bases are. Bases accept protons. So if we have this reaction where ammonia is put into water, we can say, well, base accepts a proton. Well, the only thing we have is this water. So we'll take one of these two hydrogens from water. It's going to accept that. This would be the conjugate now acid we just formed. Conjugate acid is just formed. We have a little bit. Now this reaction does not proceed greatly to the right. It is more, if I make a maybe more emboldened arrow, it's more to the left. But we have a little bit of this hydroxide anion, and you'll notice it's the opposite charge of H3O+. So it's a basic solution we would have because this reaction gives a little bit of the ammonium ion and hydroxide ion. This would be our conjugate acid, this is our base, and this would be our acid in this reaction. It's what's donating the proton to ammonia. So let's look at another problem. And I forgot, litmus paper blue for basic. It's sort of a bitter. If you put it in your fingers, this kind of solution will get slippery. And it would be a weak electrolyte in this case. If we had a strong base that gave ions, it'd be, of course, a strong electrolyte. Let's look at this reaction here and see if we can identify who's the acid, who's the base, and talk about conjugate relationships. It says circle the base and the conjugate acid in the reaction below. So if we look at this reaction, I'll kind of highlight this guy right here. We notice that on the left side, the reagent side, he's neutral. But on the other side, and this was just didn't have enough room, this is our product. We notice it's accepted a proton at this nitrogen. It had 2, now it has 3. So this accepted a proton, so this will be the base. Circle that. This is the conjugate acid. This is, again, what's made from this is kind of how that works. Conjugate means kind of yoked. So we can say these are yoked together, and this would be that base with the proton, so it's now called the conjugate acid. If we go backwards, you give up a proton back to hydroxide and make water. That's why it's called conjugate acid. This would be our acid, because we notice it's gone from having a hydrogen or a proton to having just NO2 minus left over. So those are the relationships, acid, base, and our conjugate acid left on the other side. Now we need to look at structure versus acidity. So you can look at sometimes structures of a compound and say, oh, I think it'll be more acidic or less acidic based on the structure that you see. So for example, we have acetic acid here, but it has 3 chlorines replacing what would have been hydrogens here. Well, all those chlorines are pulling electron density away from this carbon through the sigma bonds, or through the single bonds. They're more electronegative than the carbon. So this carbon would become very partially positive. And if it becomes very partially positive, then it's going to actually pull more, not less, because he's hurting for electrons, so he pulls from this carbon. And so overall, electron density is being pulled towards this trichloro group here, this carbon trichloride group, and it's pulling away from this oxygen. Well, if it's pulling away from this oxygen, this hydrogen becomes more acidic. It becomes more partially positive because we're pulling all the electrons down into this side. So you kind of show that through an electrostatic potential map, that we have a pulling of electrons away from this proton, making it more acidic. So we can sort of follow that idea when we look at these structures here. It says circle which of the following in each pair is more acidic. So we're looking at this proton as being what's given up is the acidic proton. But what effect would these chlorines have on the acidity of these protons? Well, we notice this chlorine's right off of this carbon connected to the carbon-oxygen double bond. So it's closer in proximity than this chlorine to this oxygen-hydrogen bond. So we would say this is probably the more acidic because the chlorine is closer to the group that's going to be acidic. And over here, they're the same distance, the fluorines and the chlorines, from the hydrogen that we're trying to donate. But we notice these fluorines, and we should know that the fluorine is more electronegative than the chlorine. it means it's pulling more. So we would expect this to be more acidic because the fluorines are, again, just more electronegative than the chlorines. So this is what chemists can do when they look at structures, is they can anticipate which one's going to be more acidic based on their understanding of the structure. And last but not least, if we look at HBr and HCl, we might say, okay, the chlorine we said is not as electronegative as a fluorine, but the chlorine is more electronegative than the bromine. Now, I want to be careful. We have a little bit of an exception here to the rule, go with the one that's more electronegative. If you're affecting just a carbon that's nearby that hydrogen, then yes, go with the more electronegative. But if the hydrogen, hear me out, is directly bonded to your halogen, then what we do is we consider the stability of the anion. And if we draw the anions formed after these give up their proton, the bromide is more stable with the negative charge over a greater area than the chloride. The chloride is smaller. Chloride is a smaller species than the bromide. So when it's directly bonded to the halogen, it's the bigger halogen that's more stable, and this would be the more acidic, would be this HBr. If it's directly bonded. Now again, if the chlorines were here and the bromines were here, we'd go with the one that's more electronegative because it's affecting the bonding within the structure, but it's not directly bonded to the hydrogen we're considering as acidic. That's kind of an important point when it comes to halogens. All right. I think I'm going to stop with this video at this point, looking at another way of defining acid-base chemistry. We call it Lewis acid-base terminology. And again, we're looking at, though, the same reaction. So it's important to remember that we can still consider acid with water to make some products, but we just kind of redefined how we, I guess, look at an acid-base reaction. So it's important to kind of know Lewis acid-base chemistry jargon. Lewis acids, we say, it's not so much about the proton, though that's the currency for most acid-base reactions. That's what's transferred. In some cases, we don't have a proton, but we still have what's considered an acid-base reaction according to Lewis acid-base theory. Lewis acids are those that accept, they are electron pair acceptors. The Lewis acid is an electron pair acceptor, and the Lewis base is an electron pair donor. So let's take this reaction between a strong acid and acetic acid, which is a weak acid. So what kind of reaction could we expect here? Well, the stronger acid, being stronger, will donate a proton to the acetic acid. So I'm still going to go ahead and draw, according to Bronsted-Lowry kind of idea, what we make. And for reasons I'm not going to get into right now, we would actually put the proton on the oxygen here that's donated from the acid, and we would then leave this as HSO4 minus because that would be the conjugate base left, as this gives up a proton to the weaker acid. So that's the Bronsted-Lowry view. This donated a proton, donates proton. This accepted the proton. But let's look at it in the Lewis acid-base definition. And let's make sure we follow the rule. Lewis acid says, hey, Lewis acid is electron pair acceptor. So we can say that when we give up that proton, we have one more lone pair on this oxygen. It's not going to have that H bonded to it anymore. So it accepts, or has to take on, two dots where it had that bonded to an H. And we'll look at that in some other reactions. We'll see how that's the case. So the Lewis acid donates a lone pair. And now this, we can say the Lewis base is an electron pair donor. So his lone pair is going to go to a line. It turns into a line. It had a lone pair, but it donated that to the hydrogen so it could bond or dock at that site. So if we drew the sulfate out again, we would say, oh, it used to have two hydrogens, but now it has just one. I'm going off the screen. And we had a lone pair that is now formed as it gives up one of those hydrogens. So we'll see. You don't use it too much, but Lewis acid-base chemistry is really important when you don't have a proton transferred at all in the reaction. So we'll have a few cases we'll look at in class where we don't have a proton transferred at all, but you still follow the Lewis acid-base chemistry rules. And what are they again? The acid is electron pair acceptor, so he gains an electron pair. The Lewis acid base loses a lone pair because he's donating it to that hydrogen. I'm going to stop there. We'll get into the consideration of pH and how we define the acidity of a acid based on pH. Thanks. Bye-bye.